The satellite that I'll be talking to you about today is called the SWOT mission. So it stands for the Surface Water and Ocean Topography Mission. And I'm going to sort of spin it. I'll probably tell you a lot about different things that are happening with the mission, but I wanted to kind of focus on some of the geomorphic capabilities that we have since we have 1 year of data, which is kind of nice for if you're thinking about geomorph and sort of the year average conditions that you might see in rivers. The SWOT mission is a joint mission between NASA, CNES, which is the French Space Agency, CSA, the Canadians, and UK. And what's kind of weird about this instrument is that it's built basically from the ground up to be a hydrology sensing satellite. It's a near nadir, so very close to looking straight down, Ka band radar. It's an active radar. And Ka band is kind of a weird, we usually use it for communication satellites and things like that. It's a very fine, very small wavelength, 8 millimeter wavelength. And basically it's being emitted, I'm gonna try to use my mouse here just so that everyone online can see. But essentially it's emitted from a number of different transmitters along this antenna on both sides here. This is a 10-meter boom. And essentially what that does is creates it's an interferogram. It's a pattern across the landscape. And so when the ground is flat, it looks a certain way. And when it gets sort of curvy, it looks a little different way. And by tracking how those change over time, you can get things like essentially depths of field. So this is SWOT is NASA's first and only hydrology dedicated satellite. And the whole point is really to measure coincident surface water extent and height. We want to do width or area and height at the same time. And as part of that, in NASA parlance, there's all these science requirements. There's sort of it's a line in the sand, essentially, when you say, okay, these science things that we want to do with the satellite, it's going to cost this much. And you draw a line in the sand and say, this is the minimum of what we need to be able to meet those science requirements. And that's what these are. One of the big ones I'll just point out here is, so WSE stands for water surface elevation. And basically the RMS, or 1 sigma, so root mean square error, is supposed to be 10 centimeters over about a 1 square kilometer area. So that goes for both lakes, rivers, oceans, that sort of thing. So that's pretty, if you think about 10 centimeters over it's better than it's worse than you can do with say an RTK GPS or a survey grade GPS, but it's still pretty hard to do from space, right? That's a high requirement. Slope is quite a bit better than that even. So that's 1.7 centimeters per kilometer. And extent is quite a bit worse, right? Because that's one thing about our active radar is that you can't do extent quite as well as you might want to. One thing about that is that often people get a little confused about this, that these sort of requirements apply to rivers greater than 100 meters wide and lakes greater than 250 meters by 250 meters. And the only reason that, so a lot of people will say, SWOT doesn't work for rivers smaller than 100 meters. But actually this is just because if you take a 10-kilometer reach at 100 meters width, that gets 1 square kilometer. Okay, so that's the only reason that we use 100 meters as a cutoff for rivers. And that's just for this science extents. That's just for evaluating this. So SWOT sees things that are much, much smaller than that. We've seen things as small as 5 meters wide. I'd say that's a little probably dubious. You get higher errors on that, but you can do things that are 10, 20 meters wide, things like that. It's just the science requirements don't apply to them per se. And it launched in December 16th, 2022. Here's what that looks like. Has anybody ever been to a NASA launch? If you haven't been, you got to go. Wherever you are, if you're near Florida or near, Santa Barbara, you got to go to one. I was a little dubious. I went to this one, and I was a little dubious when we first sort of signed up, and then having gone there and seen it, it was like top 5 life experience. When I'm with my wife, I say it's top 5, and then when she's not there and marriage and kids sort of aren't in the mix, then it moves up a little bit. But it's a very amazing life experience. So this is a Falcon 9. It launched it on the night of December 16th, and then turned around and landed right next door. We are about a kilometer away from this. Actually, it might be. I don't think it's the lights over there in the distance, but it's something like that. We can see the rockets sticking up. One thing for folks who aren't familiar with remote sensing, like why would we want to do radar, right? We can see Google Earth, you can see a whole bunch of different images of sort of water levels changing over time, or at least extents changing over time. I think this image is kind of nice here to display why we might want to use a different instrument. This is basically a day on Earth, right? So half the time the world is dark, right? It's at night. In the daylight portion of the world, about half of that is not visible because of clouds. So out of every pass that a satellite does, an optical satellite does, basically 1 out of every 4 passes can be used for doing extent. And oftentimes as you might expect, well, for example, here in Portland, or just in places that tend to be rainy, you often get whole chunks of time that you just don't get any optical passes. And particularly if we're interested in, say, floods or something like that, which is usually when it's cloudy, you can't use optical image that way. So with radar, active radar, you can see through clouds, you can have to see through most rain, and you can see at night. So rather than getting 1 out of every 4 passes, we get actually every pass that we see. So SWOT is another kind of way to think about SWOT is it's a wide swath altimeter. So it's similar to point altimeters. There's ISAT, ISAT2, there's the Sentinel 2s or Sentinels that have a Jason class altimeter on them. SWOT actually does have a Jason class altimeter on it. That's this thing right in the middle. That's how we've done like sea level rise altimetry for the last 30 years. What's interesting about SWOT are these 2 big wings that come off to the side, and they create these wide swath altimeters. So it does altimetry essentially out to the size of the instrument. And as you can maybe guess, this is not really drawn to scale. That's a 10-meter boom on the satellite, and that's a 120-kilometer swath. Okay, so, but basically there are the 2 50-kilometer swaths here on the side that we're going to be mostly looking at here. SWOT has in terms of temporal repeats, it has a 21-day orbit repeat time. And I say orbit repeat time because this also is a little confusing for people because a lot of folks say, oh, it's a 21-day repeat cycle. And you go, well, kinda. It's a 21-day repeat cycle in that it repeats the first orbit every 21 days. But depending on where you are in the world, you can get many, many more passes than that for 21 days. So on the right here is just a plot essentially of how many times SWOT is seeing the surface for 21 days. And as you go from the equator, which is relatively sparse, on the order of 1 to 2 passes per 21 days, as you go up in latitude, so either north or south of the equator, you get more and more passes. And so parts of Greenland, for example, have as many as 8 to 9 passes per 21 days. If you're doing anything in the Arctic, it's amazing. It's every couple of days. In the temperate U.S., we're talking about 2 to 4 passes per 21 days. So that makes it a lot more useful, about every week, something like that, 10 days to a week in the temperate regions. And that's not by mistake, right? SWOT, you have to sort of justify these things as to what they're going to do for you scientifically. And really, SWOT is kind of, if you think about this as sort of a space versus time plot of just different hydrologic events that occur. SWOT is chosen to basically try to estimate the annual water cycle for most places on Earth, right? So we're not going to be able to do things like climatic variability because it's not going to be, well, who knows? We'll see how long it lasts, but it's not on the order of 10 years or more up here. It's also not going to be able to do things that are like, rain events, really quick flash floods, even hurricanes sometimes. SWOT's probably not going to be able to see it unless you're a little lucky. It's really more set for like these kind of longer, slower things, the monsoon cycles, snowmelt cycles, kind of groundwater as you go through the year. So that's kind of a good thing to remember. It's really kind of every 10 days, you're really going to miss a lot, but you get kind of the big picture views. So SWOT for lakes is really exciting. You can think of lakes as little reflectors into space. They're really easy to see for SWOT. And one way to think about this is a Lake Popo in Bolivia. It's a kind of ephemeral lake that goes up and down quite a lot each year. And this is a kind of an early take on what SWOT could see. And essentially what you get is a kind kind of like bathtub rings, right? So you get bathtub rings of height and extent each time it goes over. And what you can do from that is create essentially like a DEM of what that lake bathymetry looks like, as long as it's above water, put it that way, or it has water in it. And what is neat about that is that creates kind of a key that then we can go back in time to a lot of our other satellite imagery and say, okay, I had a surface area of X, whatever it was, what was the height? And really what we're interested in here is what's the changing capacity, right? Changing volume. If you're trying to do a water budget or something like that. That's really kind of the key that we use all sorts of proxies right now to try to get that. Another use of that, this is a GLOF that's right above McCarthy. This is the GLOF that released this year. This is an old slide, but this is the GLOF that released this year and wrecked a bunch of McCarthy earlier this summer. And so I can pretty clearly see that pretty often. So sort of GLOFs, these are more kind of quick moving, rather ephemeral features on the landscape. And we go from something like 3,000 measured lakes to about 6 million with SWOT. So, the astronomers have James Webb, and for hydrologists, we have SWOT, right? So it's about 1,000 times better than what we can do right now. It's a really nice tool for us for a bunch of things, lakes included. On the river side, probably one of the bigger things that you'll hear coming out of SWOT is this discharge from space, which sounds a little outrageous. I don't know. I always think of pigs from space or something from the Sesame Street. But basically, it's how do you determine discharge from ungauged watersheds? And this plot down here is just showing the places that we have a relatively good handle on how much fresh water gets discharged to oceans, right? So we know pretty well, like the United States is great. We know pretty well Canada, Alaska. Some parts of South America, we have a pretty good idea of how much is going out to the ocean. But a huge chunk of the world does not share their discharge data, right? Oftentimes the data that we have is very old, if we have any at all. And so part of the justification of SWOT is trying to do this estimates of how much fresh water is coming off the continents. And to do that, there's been a whole class of different algorithms that have been designed. Of them, not all of them are McFly algorithms, but a bunch of them are. So McFly, I don't know how many of you have seen Back to the Future. Maybe not many, but it was named after that. But they stand for mass conserved flow law inversions. And essentially all that means is just that you take a reach and you say, okay, the input into it is the same as the stuff coming out of it, and you have multiple reaches in a row, and just say, okay, that kind of tamps down on the errors essentially. And so you assume that it's the same discharge for all of those different reaches. It might be just 3 in a row or something like that. And that helps you really kind of hone in on what you think the discharge might be. We've had all these different Pepsi challenges, like kind of blind taste tests essentially. That's kind of looks like this. These are the blue lines there are the places that SWOT is going to be calculating discharge or is calculating discharge right now. And this is from a paper back in 2016 and just showing some of the ranges of different McFly algorithms. And you can see there's a huge range, right? So there's this little blue one down here. There's this orange one up here. They've gotten a bit better than this. And then truth is this black dashed line, right? So generally, if you're within about 30% of what actual discharge is, you're doing pretty well, which you might think is not great, but we literally have no idea how much discharge is coming off of any of these. We have no way of constraining all the hydrologic models that are being run for example, climate models. So it's definitely an improvement, and I think we'll see a lot of improvement as SWOT goes on. We've already seen that actually. So yeah, about 210,000 predefined reaches of about 10 kilometers each. That's kind of what you see in those blue lines up there. And they tend to be kind of the bigger rivers, really. We're not really kind of messing around with the smaller things that we might have higher uncertainties on. A little bit how that works. This is kind of my take, my kind of quick summary. It's more complicated than this, but this is a quick, easy introduction to how this works. Just that discharge is equal to, average velocity times the cross-sectional area. And typically when we're doing a conventional measurement, we go out and we measure bathymetry in a place, we give it a discharge, say it's a flood discharge or low flow or something like that. And we also give it a resistance that we kind of guess essentially, or try to calibrate. And then the outputs from that are basically velocity and water elevation, right? So it looks something like this. It could be like a hydrodynamic model or HEC-RAS or something like that. What SWOT is doing is a little different. It's basically, you start with the water surface elevation and you do some estimates, some guesses essentially of resistance to get velocity. And you can estimate bathymetry and discharge, right? So it looks something like this. You kind of guess you measure the water surface, you measure the slope, and then you try to guess what the bathymetry is. That's essentially kind of how the McFly, but it's called an inversion. We're measuring the water surface and trying to invert for the bathymetry. And I'll just pose this, what about rivers where you have a gauge? This is mostly for places that we don't have a gauge, but what about rivers with a gauge? It really makes it a lot simpler, right? We have essentially one unknown and one thing that we want to calculate and one equation. And so it makes it a lot easier. I'll talk about that in a second. Any questions so far? Okay, we'll get into more exciting stuff here in a second. This is just the intro, basically. In terms of the timeline, so SWOT was launched in December of 2022. We had a checkout commissioning phase that lasted until March of 2023. And then we had this fast sampling orbit, which I'm going to mention a little bit because it pertains to places around here, particularly Portland, that lasted until midsummer. And then basically the science orbit, which is that 21-day orbit that we were looking at earlier. Let's skip that. All right, this is what the fast sampling orbit looks like. And you can see that stripe on the left side, on the west side of the coast here, going up from Northern California over the Klamath, Rogue, up to Willamette, and over Portland. It goes up right next to Seattle and then up into BC and beyond. So this is where a lot of, this is a one-day sampling from March to July 2023. Pretty interesting data set that basically no one has really looked at other than a bunch of people on the mission side of things. And so if you're interested in something like this, let me know, or go look at it yourself. There's a bunch of cool stuff that happened during that time period. There obviously are other places where that happened, but I think, in terms of not being frozen and lots of interesting dynamics that happen, there's a bunch to look at in there. This is what the 21-day orbit looks like. So relatively complete coverage over most of the continental US. So let's look at some data. So the important thing about SWOT data is that to try to keep in mind that there's a bunch of different types of SWOT data. So there's a bunch of different data products that come out of SWOT. And the sort of main thing that is on the expert level side of things is called the PXE, or the PXE cloud, pixel cloud. It's very similar to what you'd think of as like a LiDAR point cloud, but it's made out of pixels from radar products. And it looks just like a LiDAR point cloud or something like that. It's very dense. They come in 50 by 50 kilometer tiles. It's just a ton of data. And so it's pretty hard to use. It's definitely more on the expert level. But things that are downstream from that get processed from that PXE product are raster products. So if you've taken your GIS class already, you know what those are. They're pretty easy. They tend to cover really big areas and are a nice, easy, quick way to just load up and look at a bunch of data. There's also vector products. So Lake SP is basically just, you think of essentially a polygon around SWOT points and then summarized to a single point and an extent. I showed some of those earlier. So reservoirs, lakes, that sort of thing. And then the thing that I'm going to talk a little bit more about today is this River SP. There's also a vector product. It's a shapefile. And it comes in two flavors. There's a reach value for that and then a node value. So every 200 meters on most major rivers in the world, we have this node data and reach data. This is what a PXE looks like, or a PXE tile looks like. This is one of the first ones that we looked at. This is on the Yukon River just before it goes into the Yukon Delta. And I think it's nice because it highlights a bunch of the problems that happen here. So you can see that, so sigma naught is essentially backscatter to the instrument. So it tells you there's probably high likelihood that there's water there. What you might notice is that there's a lot of different water bodies all kind of mushed together, right? So there's a big river. You can kind of see that. That's the Yukon there. That's 3 kilometers wide in some spots. There's a whole bunch of water bodies. So again, this is a 50 by 50 kilometer tile. It's not very big, kind of globally, but there's a lot of water bodies in there. And the problem here is going from this to like a vector product where you separate out, you can say, so you have to design an algorithm that says, here's where the river is, and here's where the lakes are. Okay, globally, one algorithm. it is quite hard. You can see, for example, let me get this here. So here you have some floodplain water bodies that are right next to the river. Those are hard. These might be, leftover parts of the old channel that are, again, perched next to the river. And it's very easy for the algorithms to basically take these sort of floodplain features and stick them into the river product. So there's been a lot of work in trying to like pull those out. You can kind of see this little, when I was talking about the sort of smaller features that you can start to see. So that's 10 meters wide, that little tiny thing there. I think maybe it's 15 meters wide. I can't remember right now. But it's a really small feature, right? And basically we're trying to, the sort of algorithm's job is to try to separate these things out. We can try to do like, individual things on individual rivers rather than just looking at the whole mass of different points like this. But that's essentially what the kind of raw data looks like. This is just what is called a right look. So the nadir is right here. We usually cut out the first 10 kilometers, about that much there, and then just look at from here on over. So tons of data. We don't really have anything else like this in the world. So it's pretty useful. I'll show you something else. This is something that no one has ever seen before. So this is the Mississippi River. This goes from Memphis down to Baton Rouge. So here's Baton Rouge, here's New Orleans down here. This is a profile, a measured profile, observed profile on July 29th, 2023 of the whole Mississippi River. That whole thing, right? Vicksburg is right here. Some things that you can see here. So this is just pulling in the Arkansas River confluence. This is kind of a famous place for particularly Army Corps because it often, depending on which river is contributing more water, the water will flow down the Mississippi, jump over, and then flow down the Arkansas as well. Or sometimes when the Arkansas is high, it'll flow down the Arkansas and jump over the Mississippi and flow down the Mississippi. There's all sorts of weird, interactions. This is with the sort of poster child for why we needed two-dimensional modeling from the Army Corps. But you can see a lot of the features that are on this landscape, right? You have oxbows that are perched at different elevations than the main channel. Again, this is July as the water level in the main channel is dropping, and it's leaving behind a bunch of these essentially filled oxbows out on the floodplains here. So here's another one, higher than the main channel. But just tons of data. This is just a single pass. So this takes SWOT about 20 seconds, right? It doesn't take long to create a lot of data and a lot of things that we can use. So if you're interested in, like, for example, flood modeling and trying to figure out how much water is already stored on a floodplain, SWOT's a great use for that. Here's another thing that's probably I've never seen before. This is SWOT surface water elevation measurements over North America in September of this year. It took me about an hour, maybe. So these are actual observations, right? So this is a combination of a bunch of different passes, but basically, very high in the Continental Divide area and then falling off as you get close to the coast, right? Pretty neat. Central Valley, California. Here's the Colorado down here. Here's the Salt. Here's the Columbia. Tons of things to look at in here. What we're going to do here for the next couple slides is just zoom in to the Colorado and just look at what are some things we could do here. So again, here's just pulling out just the Colorado data. We have Lake Mead, we have Lake Powell, we have Flame Gorge Reservoir. So these are the average heights during that time period. We have a bunch of the different tributaries coming down. So this is the Colorado and the Gunnison. This is the San Juan with the Animas. This is the Salt that we were talking about earlier. This is Ruby Horse Thief. We're going to talk a little bit about Grand Canyon, which is right here. Which looks like this. So if you zoom in even further to see what these data look like compared to a measurement that was made by USGS down there, one of the reasons we were interested here is because they have a measurement in Deep Canyon, which is very hard to do. Took them, weeks to make the measurement and then years to make it sure that it was right. They had to hold the discharge from the dam constant at 8,000 CFS for 2 weeks, which is a big loss of revenue for the local hydropower. But basically, you can see how closely the measurements that SWOT has. So SWOT is the colored measurements here. They're about maybe 9 different days here, different times and days. I'm seeing July, May, September. Matches pretty well. There are some places where we do miss, and this is one of the most narrowest sections of the river here. So that's definitely, we're going to be looking at that more in detail, but it matches pretty well, from 900 kilometers up. Here's another example. This is kind of a neat one. This is from the Rhine. This is actually showing, so what I was showing before is node data. This is the PSU data, and these little red dots are surveyed in gauges along the Rhine. So these are, anybody know what these are from, the weird stair step? Anybody know what the Rhine is used for mostly? Anybody want to hazard a guess? Commerce, exactly. Yeah, it's barge traffic, right? So these are locks and dams. So they're moving grains up and down this thing. These are like little, whatever, stair steps or elevators. So they put the barge in and then they pump more water in and it floats up, and then they go to the next one, they pump it up and they pump it up. But the red dots here are basically the gauges, and the blue dots are just PSU data on top of that. Kind of neat. So they have, you can see how they have like split channels here. So they'll have, some places they have like the natural channel that they maintain for flood conveyance in particular, and they'll have a side channel that's actually the canal, but pretty neat. This just shows a little bit of the difference. When you have a split channel, the nodes go right down the middle, and it's trying to average across the two different channels. And so the nodes kind of vary, even though the PSU is looking good on either side, the nodes are trying to average it, and so they're getting it quite wrong, except when it goes to a single channel. And then it gets quite wrong as it goes to a double channel. So like right here, I think it looks good when it's a single channel, and then it splits and doesn't do a great job. So that's kind of as we'd expect, but definitely like caveats for using the summarized data rather than the PSU data. Okay, so what about oceans, lakes, and wetlands? I'm going to show a little bit of ocean data, but more than half of SWOT is about oceans. I heard someone say that thousands of PhDs will be minted from SWOT data. We're learning all sorts of things about the oceans that we had no idea. These long-held assumptions for decades that are wrong because SWOT was able to observe them. Here's one of the ones that just came out. This is was published in Science a few weeks ago. Came out during AGU, and this is a basically redone bathymetry of the world's oceans at a much higher resolution than we've ever had before. And these are displaying what are probably the most common landform on the globe, which are called the abyssal hills. So they're between a rift zone, and they kind of go out from, as you have essentially a rift to the subducting plate. And they're big, they're 300 kilometers in length, they're tens of kilometers wide. And essentially you can see these on the surface of the ocean by the deformation and gravity that's pulling water down into these little pits, essentially. And SWOT can see that. And this is like a huge contribution for a whole bunch of reasons. But one of the interesting things from the paper is that they said that 10 SWOT passes, so a couple months or maybe 2 or 3 months of data from SWOT was better in accuracy than 30 years of traditional satellite altimetry. So, as you might imagine, all the oceanographers are really over the moon about this stuff. David Sandwell and Gerald, the two folks I work with, these two, and they've been over the moon for a long time, just like kids in a candy store. I'm sure we're going to see a lot more of this coming out. So lots of interesting stuff happening there. Here's one that I did. This is, again, another thing that you'll probably never seen before. So this is a water surface map of the tide coming into San Francisco Bay. It's low in this is San Francisco, just to orient us here. This is the Sacramento San Joaquin Delta. If you've heard about the Delta smelt and sort of trying to get water to LA and all that sort of thing. These are the pumping ponds, essentially, to get water into the canals to go to LA. 30 million people or something like that depend on that water. And it almost all comes from the Sacramento. So it comes down here, it tries to go through all of these really complicated delta areas and then into the pumps down here. And the whole trick is to keep the saline water out while they're pumping the fresh water into the canal, right? So if you get any saline water, it would really ruin things. I mean, I worked here for more than 10 years, and if I just wanted one of these, this one image would have been fantastic. I mean, there's tons of stuff going on here. The salt ponds and the South Bay, the different elevations as the tide is coming into the Sassoon Marsh, different wetlands. Jill, you've worked here. This is just, it's just it was one image. That's like 10 seconds of SWOT data, but gives you a sense of kind of what's a lot of the things that are happening in a lot of different places. There's just a ton of data to be mined now. Here's some stuff from some colleagues at University of Bristol, just showing some of the, this is the tidal delays derived from SWOT. And one thing that you can see is pretty interesting. So they have down here is their tidal measurement, but here is all the delays in here, right? So this is a direct measurement from SWOT, where we're not using a model for tides. This is basically improving the tidal models, which I don't know if you know tides, but we don't have very good models in a lot of places for tides, surprisingly. So gonna be huge things happening in the tidal for near coastal regions and then into the inland areas. This is Bay of Bristol, some of the highest tides in the world. Lakes, we have kind of a similar thing. This is near where I live. These are recharge ponds along Boulder Creek. There's something like 180 different water bodies in here, and only 3 of them have gauges on them, or at least publicly available gauges. And so we have this sort of whole new scale to start looking at things that we just haven't had before. Similar sort of deal with wetlands. You know, there's some question as to how well SWOT can do in wetlands, and there's many questions still that need to be answered here. But essentially, this is these are the Everglades, right? So this is SWOT data on the left, and then on the right showing the gauge network that's here. That's one of the reasons we're working there. Is just the gauges are relatively good, and so we can take SWOT measurements and compare it to what the gauges are showing. And what's interesting here, can you see these little lines here? Those are I think they're called water conservation area, so WCAs. And they're essentially like little dams that they've put across here. But you can actually see the edge of the dam in the SWOT image, which is fantastic. And then if you compare the nearby SWOT data to each one of these gauges, it looks like this. So it's pretty close to 1-to-1. This is like all, you know, Everglades, like grasses and shrubby grasses, grassy wetlands, there it is there, and then shrub and scrub wetlands. So it's not perfect, but it's doing a pretty good job. I mean, the expense of putting these things out is very high, but SWOT does a good job of measuring what those are. So about a 6-centimeter difference between the gauge and what SWOT is measuring. Okay, so a good question is, how good are SWOT observations? To test that, we've looked at a bunch of different sites in the world. This is what we call the Tier 1 CalVal sites, calibration validation sites. And then underneath that, you can kind of see the little dots that are back here. There's a bunch of different, we call Tier 2 sites or Tier 3 sites, which are just using someone else's gauges, essentially. And so I'm just going to show mostly some data from the rivers, but essentially that looks like this, you know, near and dear to us. This is the Willamette up by Corvallis, one of our sites. And you can see that GNSS, so GPS drift data, where we go down, we float down the river, well, motor down the river, like Jill and I were doing yesterday in the cold, at the same time as a SWOT overpass, or very close to a SWOT overpass. The gray is the error bars around sort of max and min of what SWOT has measured, and then the blue is the average. And so you can see it's not perfect, but it does a pretty good job at the node level for a lot of things. You know, even our GPS sometimes doesn't do a great job. But you can see really small scale features in what the water level profile is showing, right? So we have a steeper section here, flatter section here, steeper section, flatter section, right? These are essentially the riffles for the most part. If you compare that over a really big chunk of data, so these are all pressure transducer data. These are all, I think there's, 2,400 observations total. These are just cumulative errors, basically, these different lines. And if you look at where, say, 68%, so one standard deviation on both sides, you get about 10 centimeters difference. There it is, 10 centimeters difference, 11 centimeters at the node level. So that's what we were shooting for the reach level, which is an average of 50. We're seeing essentially that kind of precision just on the node level. And here just gives you kind of a nice breakdown of different sites. The Waimakariri is a big braided river, Connecticut River. These are different types of rivers that we have used, and sort of during the time period. So the Willamette plays a big role in a lot of this, as you can see here. And then a bunch of places that only get seen during the science orbit. So up in the sort of the Arctic region. That's essentially what this data is showing us down here. Yeah, okay, I guess, yeah, this is the GNSS node data. So it's the relative difference is just a slightly different measure of how to do that. But basically using a little bit different like filtering tricks. This is with more observations, but it's incorporating more of the sort of things that we think might be going wrong. Dark water, I don't know if it says that in there. Oh, I saw it somewhere. Oh yeah, dark water. So it's incorporating essentially more of the sort of error things that we might see if you just looked at any random data. For a slope, we get very close to the 1.7, so it's 1.8 centimeters per kilometer. Some of them are worse than others, as you might expect. These are braided rivers. These are super hard to measure. You don't have a single, there's, on the Sedimentation, which is up goes into the Arctic Sea, there's as many as 10 different channels. So they're at different heights and things. So we'd expect the bigger errors for those braided rivers, and then quite a bit better for everything downstream of that, at lower slopes in particular. Okay, so what are some other science questions we can ask with SWOT data? This is kind of the fun one. Well, actually, here, a quick question. How many people, so, we have a lot of data, right, in the United States. How much river bathymetry data do you think that we have in the United States? How about 1%? Yeah, that's very close. Anybody else? A little less than 5%, yeah. So you'd think that we'd have some idea, some glimmer of how deep our rivers were, so that if we were trying to do, say, a flood model, we'd know when we were hitting the top of the banks and we were flooding out into the sort of surrounding communities. But no, we really have no idea. There's less than 5%. Most of those are the big rivers. So a lot of the rivers that have navigation on them, we have pretty good bathymetry, but everything else we essentially don't know other than the USGS gauges. So one thing that we could use SWOT for, it's not going to see all of these rivers, but some of the rivers we certainly can. If we use some of the contemporary gauge data with the SWOT measurements, you can start to estimate what the bathymetry is. And this is a study that we did a while ago. But essentially, we just said, okay, using synthetic SWOT data, how quickly can we iterate using a known discharge at different gauges? This is the Ohio River. Can we get to something that's close to what the actual bathymetry is? And it takes something like, I think, eight cycles, right? So these are like least squares sort of adjustments. And you get really close. It's like a, like 20 centimeter error. So quite good, just using the water surface elevation. So that's something that folks are going to be trying. I'm going to be trying. But what about things that are like more fine than reaches? Like, say, for example, this is actually a paper that we did on the Willamette, looking at some data over just a very short reach. This is 10 kilometers, right? So you have a kind of a glide, a riffle, pool, glide, riffle, right? So these are geomorphic units. This is kind of what the simulated SWOT looked like. And then this is if you constrain it, just recognizing that each one of those passes is an individual measurement and then smooth it accordingly, you get something like this. And you can kind of see, right? So I see a riffle here and I see a riffle there. There's some other stuff in here, some fuzz, but overall it looks pretty relatively reasonable. So there's, I think, a lot to be said for pulling out things that are much, much finer than what we thought we could see originally. So like riffles. If you're talking about fish habitat, for example, this is a key thing, right? So velocities of how much velocity a fish needs to get up and over a riffle. That's a good one. Or how much energy they might expend. Okay. Okay, so also near and dear to my heart is fluvial geomorph. And you might remember this from some of your classes already, or if you haven't taken a class from Jill, you should take a class from Jill. And Adam. Yeah, so stream power is typically calculated this way. It just means that we're doing sort of the weight of water. We're doing a proxy for the weight of water on the slope, okay? And because oftentimes we don't actually have how much water is there, we use discharge as a proxy for that. So that's what this little Q is right there, right? Whereas what we'd really like is the shear velocity, which is just kind of the depth slope product. So that looks like this. It's essentially just gravity, square root of gravity times the depth of the water times the slope of the river. And has a first order effect on a whole bunch of things, bank erosion, sediment transport, lateral migration, bar migration. But we often can't get it. And so we are kind of stuck with this stream power thing because we can actually give it a discharge. But one of the cool things about SWOT, right? So let's look at this here. So height times slope, those are direct SWOT measurements, right? Yeah, pretty close, or at least sort of close, right? We have to add in this extra little term here, which is the unmeasured part of the height that we haven't seen. So below the lowest SWOT measurement, there's some depth there that we just never measure. That's where having a little extra information can help us a lot. But we have a sort of relative version, or if it goes very low, or you can assume that that goes to 0 at low flow, then essentially it's the direct SWOT measurement of shear velocity. So I'll show you just a couple little things. This is a study that just started. It's a 4-year study that just got started a couple of months ago. But this is a SWOT pass here. This takes, I think it's about 10 minutes, something like that, maybe 12 minutes. But here, this is the Green River, just to give you, so it goes all the way across the United States and then into Mexico in one pass. We're going to be looking at a little section of the Colorado River. This is at the state line between Utah and Colorado. And this is a USGS gauge record here. So this is 15-minute data. It looks like a continuous line because it is pretty close to a continuous line. And then SWOT data here is in the orange triangles. And you can see there's a little bit of scatter, kind of like what we were expecting. Maybe 10 centimeters of error on some of those. But I just point your attention to the fact that these generally capture the peak in what this is seeing, right? The trick is that they're on different scales. So a lot of almost all of the USGS gauge network is not measured relative to any absolute measurement. So it just has an arbitrary measurement, right? 5, 10 feet, something like that. There's no elevation. You can't compare this to what the local DEM or local topography is because there's no comparison between them. Whereas SWOT gives you an absolute measurement. And so all I'm doing here is I just shifted these up and down. I basically minimized the difference between them to calculate what this would be. And so from this, I can actually tell you that at this gauge, the datum, the sort of where they think 0 is at 1,318.5 meters, right? Which is a pretty cool thing because it's very hard for USGS to do this. It's millions of dollars to be able to survey in their sort of 13,000 real-time gauges. And so SWOT can do it as is. So this is just height, right? So this is kind of telling us that we have some variation in height. Looks like it's about 1.5, almost 2 meters for the whole time. SWOT did not get some of the peak just because there was no measurement of SWOT over that time. But let's look and see how it compares if you calculate a bed shear stress. So that's similar to what we did, I was shown before with the shear velocity. So we're just combining this with slope that's measured from SWOT. Look at the difference. So this is the USGS data, and we're using the best estimate of what slope is from a desktop analysis, which is the National Hydrography data set. And what you'll notice, that looks really different, right? That looks really different than this, right? There's 100 times difference in shear stress. And that's purely because the slope in here is really bad. We kind of know in general that it can be bad. It has to do with how it's calculated essentially in the national data sets. But SWOT is measuring this just to give you a sort of sense for folks that aren't familiar with some of this. This is in newtons per square meter. And essentially that is what you need to move some small gravel. So 10 newtons is like kind of small, medium gravel, which is what the bed is. And we know it moves a lot. This is like kind of large gravel-ish. That's really realistic. That's what the bed is. We know it moves a ton. This stuff down here, you'd be lucky to move a bit of sand. This is basically the bed would not move at all here. So it's pretty clear this one is way more realistic than that. All right. Okay, so just a couple more slides here. Just showing you some of the close-ups, essentially, particularly around Portland. This is that Val. There's tons of potential here if folks are interested in some kind of a project. It'd be very cool. These little red lines here are the lake database. So these are things you can pull right out. It's just vector products. Super easy to use. So there are lots of little ones, some big ones. Obviously, the Columbia's in here, the Willamette. There's a bunch of the little streams in there. Some people have had good luck pulling out glaciers and things, so heights of glaciers, depending on how flat they are. anyway, a bunch of cool stuff that you could probably look at if folks are interested in a project. This is what the science orbit looks like. There's Portland for scale. There's Boise. And I think I zoomed in here a little bit. So some of the spots here, this is a 4 times per 21 days, that middle triangle or polygon, I guess there. Some of them were 1, some of them were 2 times per 21 days, but lots of coverage for things if you want to look at the current setup. So I think I just kind of end here that, just thinking about sort of like how to use SWOT and what sort of implications might be. One of the big problems that we have in the U.S. is that we have, our rivers are big and our agencies that manage them are small, and often many of them are involved with a single entity, a single river. And one of the neat things about SWOT is that you can measure really big chunks of river that get it close to what our management scales are. And they're kind of independent of different agencies. So for example, BLM oftentimes doesn't have quite as much money as some of the national parks. So a lot of this is the Green and the Colorado River system here. But they have to, to try to figure out what is happening on the rivers, they have these little study sites, and trying to extrapolate what is happening on those little study sites to something happening over a whole 300+ mile reach is quite hard. It's hard to justify that that's happening. But with SWOT, you can make some good assumptions about that. So anyway, I think there's a lot of examples in Oregon of how this would work too. The Deschutes, the Willamette, Columbia, John Day. There's a ton of them, and even some of the smaller rivers. So yeah, so I guess I just end and show you this slide that it's really easy to use SWOT in general. The probably easiest place to start, if you remember nothing else from the talk, is just SWOT cookbook. That's the place that's got a whole bunch of handbooks. It's got Python, Jupyter notebooks for people to use. Super easy, lots of different tips and lessons. The really super easy version is just to go to the NASA page and download some data. So that works too, but tends to be a little slower. So go check it out, see what you think. And I'll stop there and just say thanks to Jill for the invitation, and thanks for y'all for listening.